I used to build light that you couldn't see. Near-infrared organic LEDs with the emission wavelength beyond 900 nanometers. The kind of glow that doesn't register to your eyes until a sensor catches it. I love that kind of idea. The most powerful things are invisible. For 4 years at Cornell, I was one of the few material science engineering students in my class. At night, I spent time building the hardware that enables magic happen. The emitters that allow your phone to recognize your face in pitch darkness. The sensors that allow autonomous vehicle to see through a blinding fog. And that lab taught me something real quick. Magic is easy to imagine, yet materials are hard to manage. On paper, our chemistry was perfect, but in the lab, the reality was a constant battle with operational lifetime. With one unstable interface, you suddenly have exodon quenching, iron migrating, and performance collapsing. I learned that the material is only as strong as its weakest interface. Now that's the bottleneck I think AI is running into today. The future doesn't fail because the idea isn't beautiful. The future fails because materials won't cooperate. Hey, if you're interested in the future of AI, who here around isn't? Please keep in mind that the future of AI isn't governed by model capabilities alone. It's governed by 3 physical limits: compute, data, and energy. And today, I'm telling you that underneath each of that is a materials challenge. The first limit is compute efficiency. Inside every AI chip, logic and memory still sits in different physical domains, so data needs to shallowing back and forth all the time. The processors can think incredibly fast, but it generates enormous amount of energy moving bits across the interconnect, and that energy becomes heat. Push the system hard enough and it throttles. Not because it can't compute, but because it can't dissipate heat. Now, this is not a latency problem. It's a joules per bit problem. High bandwidth memory is the industry's most important response. By leveraging 3D stacking and TSVs, HBM puts compute adjacent to memory, collapsing the distance, widening the interface, and significantly improved the energy efficiency. But 3D stacking didn't remove the problem. It moved it. On scale up, HBM can't grow indefinitely. Thermal density, yield loss, power delivery caps HBM scaling. And that capacity lacks model growth. On scale out, once the memory leaves the package and has to travel across NVLink, across the racks and data centers, distance comes back. Energy per bit goes up again. You can't code your way out of this problem. This is not a software issue. It's a materials and integration limit. Until the day we have logic and memory truly co-locate, compute efficiency will always be the first wall that AI keeps running into. The second limit is data integrity. If compute is how AI thinks, data is how AI senses the world. In the physical world, data is never abstract. Data is a measurement, and every single measurement passes through materials. To understand the real world, we need stable, high-fidelity signal across multiple modalities. Vision, touch, force, depth, motion. Each is bounded by sensor physics. Take vision, for example. Cameras are still suffering from low light, glare, and thermal noises. You can't infer details that never get to the camera. Missing photons aren't a model problem. Then there's the stability challenge. Materials take on moisture, optics shift, electronic drift with heat loss and time. So the real-world input slowly changing to something different. You can train a robot to hold an egg in the lab perfectly, but 6 months later, in a real kitchen, the sensors have changed. The signal that used to mean gentle means crush. This is not the robot being confused. It's the nervous system lying. And once you have that, your data isn't just noisy, it's systematically wrong. That's why physical AI feels brittle outside of the lab. Not because the intelligence isn't there, but because the interface to reality is unstable. And what it looks like to be a data problem is underneath a material stability challenge. The third limit is energy waste. Energy is the invisible tax that everybody pays. Every wire, every contact, every interface wastes energy in the form of heat. In 2024, data center consumes roughly 415 terawatt hours, roughly 8 times of the New York City electricity consumption annually. And in the base case, IEA projects that number to be double by 2030. And most of that energy isn't used for compute. It's used for moving signals and removing heat. So we get creative. We start to talk about AI factories next to nuclear plants. We talk about small modular reactors, solar breakthroughs, geothermal, and even data centers in the space. And every single one of those solutions runs straight back into materials. Energy isn't a motor problem. It's a material science limitation problem. As long as we keep wasting energy in the form of heat, and as long as interconnects and power delivery keep setting the ceiling for performance, intelligence remains heavy, expensive, and centralized. And that's the third limit that AI will keep running into. When I was in the lab, our device worked beautifully until they meet the real world. Moisture slips through the seals, temperature swings pulled layers apart, contact corroded. And that was the first real lesson I learned. To put intelligence into the world, you need to first package it against the world. Materials have edge cases, and edge cases are where products die. So that's what we do. As material scientists, we fight the slow battles with heat, loss, and time. And once those limits move, the whole industry reorganizes. Here we are then. The next breakthrough of AI wouldn't coming from smarter models alone. It will be coming from materials that enable compute, data, energy efficient enough to scale. And in the short term, the progress will be unglamorous, but it will be critical. Better packaging, better interface, better thermal pathways, more stable substrate. In AI scale, every few percentage point of performance improving sets the difference between the demo and the deployment. In the long run, the breakthrough won't come on schedule. It will be at constraints where we've been grinding for years. Superconductors that actually works, quantum computing that are coherent enough to be stable, and materials that improve efficiency and lower loss and enable intelligence information to behave differently than what they do today. I started with the invisible light that you can't see. A glow that's beyond 900 nanometers, only a sensor could catch. And that invisible technology ended up inside billions of devices today. And the next era will be built the same way. Quietly, physically, and then all at once. So, if you're chasing your AI dream, or if you're investing in this space, please keep in mind that the future of AI isn't about what it can think. It's about whether it can survive the contact with the physical world. And that future won't be defined by models. It will be defined by materials. Thank you.